So we are going to continue. We yesterday tried to see how the representation of states can be done in the Hilbert given Hilbert space, the basis states. Now the point is that in today's class we are going to have continuous states. So in quantum mechanics, normally we have we take discrete or values, and its representation in the Hilbert space is more or less comes. But in principle, we should, the way we had in the previous class, for example, we had a denumerable basis where you can have in a denumerable basis there can be infinite one-to-one correspondence between the states and in the Hilbert space. So if it's not discrete, if it is continuous, what can be the representation of that? So for example, we can treat, for example, if let zeta be any large value, discrete large number of large number of large number of So the one modification we should make it is that we are going to have a description of a physical system. Description of a physical system. Or physical states. Sorry, states. Which is modified as far as previous section is concerned. So we are going to have system which the complete orthogonal states form a continuum. So this is the thing. So if a orthogonal state forms a continuum, normally we take that they will have a discrete correspondence. So if they form a sort of continuum, how can that altered mathematical representation, how can we have a mathematical representation for that? So what we are going to take, we are going to take zeta be a large system, large number, and rho zeta, d zeta of discrete values of zeta, discrete values of zeta in the small interval zeta and zeta plus d zeta. So what we are going to do, and if zeta is a x coordinate of the particle, so large number of discrete points they will have. So we can have this thing. So the discrete interval can be represented by this. And complete sort of orthogonal basis phi zeta prime and phi zeta in terms of brackets can be written as rho times zeta delta zeta prime zeta. So an arbitrary state can be expressed as the linear combination of the states. So if you remember yesterday, I just write it here, we just had psi of zeta, psi was written as pi zeta, psi of j, and phi I, phi j. So psi can be represented like this. The components of phi. So we can, in terms of psi, in terms of phi, can be written like this. So for a typical state, for an arbitrary state, so for an arbitrary state, the linear combination of basis states, taking just the thing from the previous definition, that psi can be written as. So now we are going to replace it by this j and this by zeta. So zeta will be phi of zeta psi. So here rho j, it will be phi zeta and phi zeta. It will be, you can also write it phi zeta, you can write it through and phi zeta. So in the limit, zeta becomes very close to together, so that sum over the continuous function can be written. If we want to have the integral form of this, how we represent state psi in terms of integral form or in terms of some function of zeta, then it will be equivalent to f of zeta will be equivalent to f of zeta rho zeta d zeta. So we can say that so in the limit we can say if we sum the limits, we can write psi can be written as psi can be written as so sorry, I'll write it here. So psi can be written as phi zeta d zeta. So in the limit of equation 3.2. So if you can give numbering to the equations, it can be this equation can be one equation. This can be equation 2 and equation 3. So in the limit equation, this equation, so this is so this is 3. So in the limiting case, this equation can be written in terms of food. How? So what we are going to do, we are going to write psi in terms of phi zeta psi in terms of phi zeta phi zeta. So similarly, if you remember, yes, this was one equation. We also wrote yesterday psi of psi prime can be, if you want to write it in terms of a complex conjugate. So if it's phi of psi star, phi of psi I, you can also write it as phi I. So this is inner product. This is simply how we can write the components of state psi in terms of phi j. So it's the inner product of these psi, its psi conjugate can be written this way. So if you are going to use these things now, we want to write psi prime in the form of some integral. So it will take the form such that psi of psi prime will be equivalent to phi zeta psi star phi zeta psi. So phi, it will be phi zeta we have previously written also in terms of rho this thing. We can write in denominator it will be phi zeta, we can write rho zeta here. That's it. And further, we can write it like so. In particular, the condition for the state psi, condition for the state psi condition for the state psi, we have a unit norm, we have a unit norm, we have a unit norm I. So if you just unit norm means the inner product of phi, this with the zeta square. It will be inner product, so it will be square of a complex conjugate. It will be square. It will be phi zeta psi of square d zeta. Now we are going to have the way we can have the way yesterday we tried to find introduce here the Bohr probabilistic idea. How we can write if we have a state psi under some measurement it becomes psi prime or phi. So how we can represent this states, these continuum states which exist between this between these two rho and rho plus d zeta and zeta plus d zeta. So how we can write this thing? How we can write the probability? So probability, for example, yesterday we saw probability of psi going to phi was phi of psi square psi phi phi. So here the probability psi going to phi zeta will be phi zeta psi square phi zeta, so it will be phi zeta cross of rho zeta d zeta. So it is again this rho zeta will be phi zeta, so if we consider this, so it will be sort of phi zeta psi whole square d zeta. So this will be the probability, and it will come out to be the essential condition for the probability will be at the end by Bohr rule or by general probability conditions. If there is a transformation of state psi to some phi, psi to phi, so the total probability will come out to be 1. It will come out to be 1. So if you remember, the wave function it can also be written nothing as if it's a sort of scalar product. Wave function can be written as a scalar product in terms of phi in terms of psi, or psi in terms of phi, or psi in terms of psi, or phi in terms of phi. So different thing. So you can say scalar product of two scalar product can be written as if you write it in terms of psi 1 psi 2, so you can write it as psi 1 psi 2 can be written as integral of psi 1 star x psi 2 star x dx. So in particular condition, if psi 1 is equal to 1 is equal to 2, then psi square x 1 is equal to so which is the probability which is located between x and x plus dx, or zeta and zeta plus d zeta, in which the state just goes from phi to psi or phi to phi prime or whatever. So the probability is 1, and the probability dp will be, if it's in terms of psi, it will be the square of amplitude, and it's the. So this interpretation was given by Bohr, and there's a section in this book. You can just check it out. Now, the point is here how we can introduce delta functions, Dirac delta functions. In the conventional sense, Dirac delta function is that it becomes a maximum at the origin and zero otherwise. So in a particular scheme of the way we define improper functions, so it can, the value can be steeper, it can go steeper such that at some point it can be maximum, and the neighboring points, the values may vanish suddenly. So in that sense, if we just use how we can use the Dirac delta definition in our representation of these continuum states, which can be very much handy. So for example, if you see delta of zeta minus zeta prime is equal to rho of zeta zeta prime, and normalization condition for the continuum states is read as delta zeta minus zeta prime. So according to this, so what the integral over this function on any smooth, so if you define an integral which is defined in terms of this improper functions, so we can define it as so it will be f of zeta. So we can define it like this. So it vanishes at all points, but at zeta is going to zeta prime, it will not vanish, or in some cases it can come out to be maximum. So so there's another way of writing this Dirac delta function. If you want to see it, so it might peak to the integral unity, but from it may not so it may not be allowed to go to zero through positive values. So you can also define this delta function by some change where delta of zeta minus zeta prime can be defined as epsilon zeta minus zeta prime less than epsilon and 0 for greater than epsilon. So according to this theorem for so it can be, so we can just change the value of this Dirac delta function here in terms of this, and which will not necessarily leave that Dirac peak. There cannot be necessarily continuity attached to it. Once we go from this, for example, say Dirac delta function, it's a peak. Once you go from this plane to this plane, it's not necessarily there will be continuity attached to once you go from one plane to another, while we are having these value of limits. Now again, the other way of writing this, so it's basically the point is we are trying to invoke this Dirac delta function in our, how we have defined zeta and zeta prime as continuum states. So these are different ways of representing them using Dirac delta function, and the other way is that of writing in terms of something called Fourier transform, which you might be aware. So using Fourier analysis, using the theorem that For a sufficiently smooth function, k going to plus minus infinity, function of x can be defined as minus infinity to infinity g of k e to the power iota k dot x, and g of k can be defined as g of k, if you just its inverse of this, it can be defined by minus infinity to infinity e to the power function of x e to the minus x dx. Now if you want to write gx, you substitute value of gx here, so it will come out to be function of x can be defined as, you can see it can be defined as 1 by 2 pi minus infinity to infinity dx prime fx prime minus infinity to infinity dk e to the power iota k x minus x prime. Or we can write delta x minus x prime can be written as dk x minus x prime. So we have done nothing, we have just, so if you just write this Dirac delta functions in terms of this Fourier thing, in terms of one component of this thing. If you write delta x minus x prime in terms of this thing, so this is another way of representing it. And further, we can have this value. Further, we can have this value. So we can have we can insert this convergent factor for in that integral such that it will become the same as that of so as that of if we have, if I don't have just missed this equation, we can write it as delta zeta minus zeta prime 1 by epsilon pi exponential of zeta minus zeta square by epsilon square. So this, I missed this. So we can write it like this. So we can here this Dirac delta function here can also be under this modification of that exponential functions, and with these change of limits, we can still define this Dirac delta function. But the thing is that once we use Fourier transforms and a particular how we invoke delta functions as part of this Fourier transforms, so this equation it will reduce to this equation, which shows that unity of different not methods how we can represent these continuum states, which are basically representation of states going from state A to state B in a given they may in a given continuum which correspond to those discrete states. So that's it. So these are different representations. One is Dirac delta way of representing the thing, and another is the Fourier transforms. How we can invoke Fourier transforms, where we have a function and a writing function in terms of inverse functions. Both we can represent these continuum states. And also there is another more rigorous approach in literature that's also known as distributions, theory of distributions, which was invoked by mathematician Lawrence Schwartz. So here we do not we leave away this way of defining delta function in terms of functions. We leave that statement. Rather, we'll write them in terms of some in terms of integrals, we can also represent them in some advanced way using Taylor functions. So today's, so I just quick start here. So today's class was more or less how we can represent these continuous states. Thanks. Stop.